All right, so I'd like to introduce Felix Heide. He's the CTO co-founder of a startup called Algolux, which is basically doing automobile vision systems. His talk today is going to be about an IEEE standard, which is looking at different types of low light images and things like this. So he's going to talk about some of the efforts that they're doing for that. So welcome, Felix.
Yep. Yeah, thank you very much for the kind introduction. So imaging and vision systems, especially in an automotive context, have to deal with extreme imaging scenarios, going from very, very high light levels due to sunlight illumination, highly reflective objects, all the way down to extreme low light objects in the peripheries. And all of these very challenging, hard imaging conditions have severe impacts, especially in the automotive world. So other than cell phone imaging here, we really deal about systems that are safety critical. And here's an example. Here's a very extreme example just to show you the effect on state-of-the-art vision, higher level image analysis. On the left side, you see an image, which is an ultra-low light image acquired of a scene out in Montreal. And so this is an image which is a contrast normalized image, so very, very low signal here. You can see that very, very severe noise. You see streak artifacts from the sensor, and you can see here that a state-of-the-art detector, such as faster RCNN, some modification to achieve state-of-the-art performance on COCO and other JPEG data sets, actually completely fails in this scenario. On the right side, you see a bunch of more challenging cases where you have reflections on the road here, artificially severe aberrations, but you can get similar cases in realistic automotive systems all the time. So you can see here that here's a pretty fast one. Google's SSD also fails in these scenarios here. So let's look at a common automotive test scene that is used for assessing the image quality of an automotive imaging system and vision system. So what we have here in this test scene, what's simulated here, are optical aberrations, such as the one that I showed you, an extreme case on the previous slide. So you see the effect of headlights on the optics, introducing severe glare in this case, and spread of a point spread function because of the high illumination. What you can also see here are, and this especially matters for rear view cameras, optical geometric distortion, severe chromatic aberrations due to severe off-axis PSF spread. What you can also evaluate with such a test scene to a certain extent is the naturalness of the scene. Sharpness, of course, the traditional checkerboard pattern features can be seen in the scene here. Fairly extreme range of contrast levels can be measured. Color fidelity, structure in shadows, extremely important to perform vision in such areas. And noise handling, of course, in such low light scenes where it really matters and traditional ISPs fail. There's utility embedded in such test screens. And especially traffic signs and other content-specific, automotive-specific objects are embedded in this test scene here. And of course, there's more ray patterns. And this is only one static test scene. So it's important to realize that all of these metrics, these KPIs that we can measure on such a test scene are only for a static scene. And it's in perfect condition, so we haven't even explored parameter variation such as temperature of the camera. For dynamic scenes, you can imagine that there's other effects, and I'll get into this. So this brings us to an important question. Now, let's say if we have such a standard established test scenario, when do we decide that an imaging system that produces images that are in fact good enough for viewing? What is even good enough for viewing? And even more so, how do we decide that the images spit out after the ISP are in fact proper and good and keep all the information that is necessary to perform accurate and robust computer vision? So for viewing, the cell phone industry has established this system of the golden eye. You have imaging experts that can evaluate, that can tell you, okay, this is an image that is good. This is the tone mapping that we want, just exactly the right white balancing, other dynamic control parameters are exactly as they wanted. But for computer vision, it's not clear anymore. Like, there's no experts that can tell you, okay, this is a perfect image other than, okay, well, keep all the information in. So basically, don't do any processing, throw away all the ISP and so forth. And so this, because of the safety critical nature of this topic, because it is critical to saving lives, it's essential to come up with a standard in the industry that characterizes image quality for automotive systems and brings in standards that define measurement procedures that everyone can agree on, and KPIs associated with those measurement procedures that can then be measured in the unified framework. And then all the OEMs can set their different thresholds for these individual KPIs. But in order to bring a minimal level of safety to this field, especially on the imaging chain, these procedures are necessary. And this is the idea, the reason behind the IEEE P2020 working group, which addresses two subproblems of the imaging chain. The first one is viewing applications, so images viewed by human observers through a screen in car. And the second application is machine vision applications, so self-acting ADAS and fully autonomous systems. And luckily, a large number of industry leaders have subscribed and are participating in P2020 and contribute to the standard committee. There's a number of subgroups that address individual subproblems of this overarching big problem of characterizing image quality and computer vision quality as it relates to an imaging system. There's a subgroup addressing LED flickers, dynamic artifacts due to LED lighting. There's image quality for viewing, image quality for computer vision, and interfacing, and a few other more customer-facing subgroups. So let's start and go through the individual efforts, just to give you an overview, just to walk you through what is being addressed in this in the standard. So LED flicker is a dynamic artifact of sampling LED illumination signals in the wild. So most of our traffic signs, illumination signs, outdoor illumination are LED-based these days, and LEDs are driven with pulse width modulation. We have like short pulses, unfortunately exactly at a frequency that's pretty close to the sampling frequency of a camera, so like 60, 70 hertz. They're pulsed and switched on and off with a very short duty cycle. So now if you have a short duty cycle exposure in your camera system let's say like 30 frames per second, then something that is shown here on the top, an effect can happen that you miss certain of these pulses. And there's various different sensor technologies and ISP technologies to try to mitigate flicker and alleviate it. But the important thing is that there first also has to be a method to measure and characterize flicker and how it affects image quality and computer vision. There's even a further subtlety to this if you think about rolling shutter cameras, and this of course also affects not only the temporal behavior of the capture, but also spatially due to the rolling shutter exposure in the camera. We can get quite severe streak artifacts in this setting here where we have a fairly uniform LED illuminated backstream. And you can see here, this is an interesting example on the top right. Here's a car, and I'm going to play it again, which has, in fact, interestingly, two different drivers for the pulse width modulation in the headlights. So you can see here I'm going to play this again. In the very last frame, you see the right seemingly blinker going on, and you can see here it's completely different beating patterns that you measure here. And in fact, the car was not turning on its turn signal. This can be extremely challenging and hard to handle in systems, because even semantic context is only helping to a certain extent here. Then on the bottom, you see a classical example where you have the illumination screen of the bus signal here turning on, if it would play. I guess it doesn't want to play. But the main goal here is that the P2020 working group designs a procedure to measure LED flicker, and also provide interfaces to evaluate how this affects computer vision systems and detection in challenging scenarios and use cases that matter in the automotive world. The next subfield out of P2020 would be imaging for viewing applications, or designing KPIs for viewing applications. And here the standard really targets glass to glass. So that means incoming light field, propagating that all the way to a display, which is then emitting signals which are perceived by a human and analyzed as an image. And here the standard really borrows a lot of the measurement techniques that had been previously used in other domains, such as cell phone imaging. There's CPIQ, which has a number of sharpness, texture metrics, color metrics. But we also add additional metrics and on use case specific problems such as LED flicker, tone mapping specifically to automotive situations is an important topic. And all of these KPIs have to be measured in a very different way, because now it's not the case anymore that we just have to provide pleasing image quality, just make your system work as if you would put an iPhone there and produce nice tone map results, but in fact, these systems have to produce outputs which are interpretable and give you enough information so that you can make a good decision. And here's an example that addresses this. So here's a typical automotive image capture, and here is two different tunings of this imaging system. Here in this case, the ISP on the left side tuned differently than on the right side, where on the right side we tune the system for nice, perceptually pleasing images. So we suppress a lot of noise in the frames. On the left side, you can see here that the capture still contains a lot of noise, but also contains a lot of detail. So we have to handle this trade-off of information versus visual aesthetics in the standard. And this brings me to defining KPIs, defining metrics and procedures to measure such metrics for computer vision. And so this is an interesting subsystem that gets characterized in P2020. So rather than looking at a system really completely end-to-end, taking incoming light field in varicination, propagating it through the windshield lens, sampling on the sensor, ISP, then the computer vision trunk, the system looks at the front part. So it only looks at the part which can characterize all the way from the scene illumination to an output by an ISP system. So that gives you a huge number of parameters that you can play with, that you can also characterize. So being the optics, the sensors, the processing as it relates to HDR fusion, for example, sensor parameters such as quantum well can be put into the analysis, as well as other higher level ISP parameters. But stopping there makes sense because you want to isolate, at least characterize the system independently of other further higher level tasks as such. And so here's an example of a typical imaging chain, which is addressed in P2020. So here we have a scene, which is modeled just by illumination, gets propagated through the scene, have an incoming light field that gets propagated through the windshield. Then the windshield can introduce severe optical effects such as glare, shown here on the right side. Then goes through the camera optics. On the imager, it gets sampled, converted into a digital number, some noise properties that are borrowed from a different standard. Then then gets piped, then the measurements get piped through an ISP that has various processing blocks, same as eking, denoising, tone mapping once it gets stored on memory. And all of these individual blocks in this overall imaging sensing chain have severe outcomes on the overall image quality and the performance in computer vision. So on the right side you see here an example where, for example, in the windshield, severe glare was introduced to do headlight illumination in a tunnel here. And so to measure these effects and the effect of parameters of each of these blocks on the overall computer vision performance, the standard has developed a few metrics, which are mostly looking at gradients, essentially. So we have local contrast gradients, which measure the local contrast and quantify that. Color separation metrics, so basically just how well can you separate clusters, different measurements according to color. Flicker mitigation probabilities, and geometric separation, so overlap, and other geometric metrics which are introduced. And this allows us then to isolate, to characterize the overall system in isolation without a higher level processing block. The standard is about to publish a white paper, so it's almost done with like a first set of overview level metrics, which give you a rough impression of what's happening. And so I want to talk about this a little bit because it's important to raise awareness for this topic. Would like to invite everyone who wants to contribute. And so the white paper, which should be published in sort of the next couple of weeks, gives you an overview of where you could contribute, where you could fit in. And with that, I'd like to thank you and give for a couple of seconds just a brief overview about what Algolux is. So Algolux is a small company in Montreal, and we look exactly at these challenging vision scenarios, at extreme low light, adverse weather conditions, everywhere where your current systems completely fail. And with that, I'd like to thank you.
Excellent. So if you have questions, please come to the microphone here. Line up at the microphone. While we're waiting, make sure that you fill out your surveys. Remember, there's actually a $100 Amazon gift card on the line there. So make sure you get your surveys filled out and turned in. There's boxes outside the room, or you can do by the registration. Go ahead. Yeah.
Thank you for the presentation. This was very informative. And I have a question about, is there any standard or any initiative to define a standard for the lens itself? So since it's the first part of the system, is there a specific attention to that?
Right. So there is an effort that looks specifically about the optical system, not only the lens, but basically the overall optical system. So windshield in combination with the objective. But that really cannot be characterized in isolation just by itself, because it affects the processing further down the line so much, right? I mean, as I showed you, we can easily model the effect of a certain windshield, certain optics, certain PSF on contrast detection probabilities, on contrast and the ability to detect certain objects. But now getting into this feedback loop where you say, okay, well, now you should design your optics in a different way. That's a different story, right? So I'm not aware of a standard, but that is an interesting field, and we in fact have a paper on that, how to learn optical systems for task-specific applications.
That's something that I would be happy to contribute, so I will connect with you.
Yeah, do that.
Hello. Hey. So in your presentation, you talk about the new KPIs for the computer vision system.
Yeah.
But is it actually, in your opinion, is it ISP or just an optical system, so optics plus sensor, whereas ISP function is sort of abstracted in computer vision that
Yeah.
can take, for example, bare raw.
Right, right. I mean, that's how you can. It depends on how you think about where you cut the system into two parts, right? Where you either say the ISP starts and where not, right? I mean, you could also say, okay, well, anything after sampling, right, after I have my raw measurement, is then some sort of processing, right? But it is important to be able to characterize systems in isolation, just to make sure that we don't lose any information and have safety critical information still be there. But that said, like the effect, we can certainly model the effect of certain capture parameters, right? For example, HDR fusion is a good example where we can actually fairly easily model the effect on what exposure settings you use, how many exposures you use, how you fuse them on things like contrast detection probabilities. That's possible. Yeah.
So HDR or WDI is where one of the key parameters.
I mean, that one you really have to take care of because it's so essential in the automotive context, right? And that is very accurately modeled.
But can you apply your KPIs, well, the vision KPIs, so you call straight to the output of the sensor? Or
Yeah, exactly. So you can do that before. You can apply them straight to the sensor, but you still sort of need a trunk of an ISP. You can basically say, okay, well, I only do, I don't know, bilinear demosaicing or something very simple, so that I just get a image on which I can measure contrast detection probabilities and other things, right? I mean, the color metrics do very easily propagate through even raw data, right? But anything else, if you look about spatial information, then you have to modify these metrics, right? I mean, one easy fix might be just introduce a stride, and then you should be fine if you talk about spatially multiplex measurements. But these assume spatially dense samples.
the mosaic is sort of something you do need.
Yeah,
Okay,
exactly. So, I mean, you could sort of say, okay, well, almost no demosaicing, right? By just introducing the stride tool, and then in your contrast detection computation, that is possible, right? And see a couple of neural network architectures that in fact do that for demosaicing, right?
Well, thank you.
How do you deal with the effect where the ISP is affecting the performance of a particular network that's doing machine vision?
Yeah.
Output?
So that is something that is very, very, very tricky, very important to address, and that is actually something that's not handled in the standard, unfortunately. But we as a company actually focus on that by building a tool that allows you to either completely replace the ISP or tune the ISP all the way end-to-end with just a mean average precision loss, for example. That is possible. But it's much more tricky than defining mid-level metrics here. So the mid-level metrics help you to define a minimum standard, but in order to get the best possible performance, you have to obviously train the system end-to-end, because there is a huge feedback from the network to the ISP parameters. And in fact, very interestingly, you need to tune your ISPs completely differently than you tune them for traditional human viewing. And in fact, also the training, which is also an interesting side comment, because we're capturing large JPEG data sets, which are all processed. It's actually not the right way to do it.
Do you foresee a time when, other than things like exposure control and control of the sensor to capture a image, that there's any ISP at all?
I do think there's a huge advantage for or a huge benefit of putting dynamic control aspects, like you say, 3A stuff into hardware. But other than that, I think there's always going to be an ISP for viewing, just because there's such a massive investment around hardware blocks, design parameters, algorithmic contributions in that area. I think we can tune these to get reasonable performance. I don't see it for computer vision.
Okay, thank you.
So the tool that you were just talking about and what you had on your last slide, is that something that you work with those companies to develop for their specific sensors, or is that something that you kind of have this tool, this package for these specific things, and then kind of just have a
Yeah, no, I mean,
implementation?
it generalized fairly well. So we have, it's obviously sensor specific, so we have to calibrate the sensor, also calibrate the optical system. And so we work with companies in the space, tier ones and OEMs, to exactly give them that capability. That's right, yeah.
Okay. Thank you.
I was wondering if there are standards, working groups, or whether Algolux itself has looked into machine vision in an aviation context, not just for driving.
Aviation, yeah, super interesting. I'm not aware of any standard. We haven't looked into aviation. We've looked into surveillance. There's a lot happening in surveillance, super important topic. Aviation would be very interesting. I'm not aware of a standard, though. So.
Okay, thanks.